So in this slide, let's just review our limits before we move on, okay? So it says here, the first one we want to find is the limit as we approach an x value of 1. So I'm talking about this one. So as I get to an x value of 1, what height am I approaching? I am approaching 3. Now, you want to always check, are you approaching it from both sides? If it doesn't specify, you have to be heading to the same place from both sides. Now, for B, C, and D, those ones all go together because it's all related to an x value of 3. So this first one here is 3 from the left. So what height are we approaching from the left? We are approaching a height of 2. So this one is 2. What height are we approaching from the right? -2. Now I'm going to jump to E because that actually goes with it as well. What is the actual function value at x equals 3? It is 1. Now let's talk about the limit. From the left side we approached 2. From the right side we approached -2. So what is the limit at 3? Does not exist. Okay, it is undefined. So for F, G, H, and I, those ones go together because they are all concerned with an x value of -2. So first, let's start with this one. So that little negative notation means we're coming in from what direction? The left. So we're going to go to an x value of -2. We're coming in from the left. What height are we approaching? I think that's -1. Okay. How about from the right? So what is our limit at -2? Yeah, we don't care about the fact that f is defined somewhere else for limits. So that will give us some information about whether the function is continuous or not, because if the limit and the function defined value is in different locations, there is a problem at the graph. But because of the fact that it's a limit, what are you going from both directions? So you'll notice that f of -2 is defined down here at -3. So that's just a little reminder about some of the limit stuff, okay? Today we are going to talk about some of the things I was just bringing up about continuity. We're going to talk about those discontinuities from last year. Last year we talked about a jump discontinuity. We talked about a infinite discontinuity, and then we talked about a hole in the graph. So there were 3 different types, and that still is going to hold true in a calculus class. But now we have some theorems and things to back it up. Our knowledge about limits we're going to use in continuity. So a function is continuous at some number a if and only if the limit matches the defined value. So the function will be continuous if the limit matches the defined value. So there are 3 things we're going to check. 3 things we're going to check. You're going to check, does f of a exist? Is a in the domain? And then what is it? So does f of a exist? Is it in the domain? And what is it? Then you are going to check the limit. Does it exist? What is it? And then do they match? Does the limit equal the function's value? If it isn't continuous, guess what? It's discontinuous. That's amazing how that works. So the limit matches the defined value if the function is continuous. So here, let's talk about on what intervals is the function continuous and why is it discontinuous. Okay. So let's talk about, for this function, this section right here. And let's assume there's an arrow there, and let's assume there's an arrow there. Okay. So from an x value of negative infinity until an x value of 1, it is continuous. Everything up to 1. And you'll notice that I have a parenthesis on the 1 because 1 is going to be an issue. So then from an x value of 1 to an x value of 3, it is continuous. Now you'll notice that 3 is a defined spot on our graph. Now we would call that it has 3 has left continuity. So it is only continuous from the left of 3 because the function comes in and hits that defined value. So, but it was only a left-sided continuity, if that makes sense. And then we have a piece from 3 to 5. And then we have a piece from 5 to infinity. So every place that there is a break, so there's a break at 1, there's a break at 3, there's a break at 5. So let's discuss the spots that it's discontinuous. So it's discontinuous when x equals 1, x equals 3, and x equals 5. And then let's talk about why. What is wrong when x equals 1? There's a hole in the graph. So that technically, mathematically, if we're talking more precisely for calculus compared to a pre-calc class, we would say that f of a does not exist. F of a does not exist. That's the problem. F of a is undefined, okay? Now let's look at x equals 3. What do we call that when that happens? There's a jump in the graph. So we could say that the left side and right doesn't match. Okay, so that's a jump in the graph. Let's talk about x equals 5. At x equals 5, the limit as we approach 5 does not equal f of 5. So we have a problem because the limit as we approach 5 and the function value at 5 is undefined. The limit exists. The limit exists. The function value exists, but they don't match. And so that is the problem we have at 5. The limit and the function value doesn't exist. So that's why when we do continuity, we have to check 3 things. What is the limit? Does it exist? What is the function value? What does it exist? Do they match? So those are the 3 things we're going to check every single time. Everybody go with that? So it says, where are the following functions discontinuous? Well, think about a fractional function. What messes that up? What messes up a fraction? Denominator. So here, x minus 2 is not allowed to equal 0. So at x equals 2, we have a discontinuity. At x equals 2, there's a discontinuity because our denominator is not allowed to equal 0. Let's look at B. Let's look at this one. As we approach 0, well, first let me draw a very rough, ugly sketch of this graph. It looks like this. What is the limit as we approach 0? What it's going to positive infinity, right? Both left and right sides are going up. What is the function value? What did they define the function to be at 0? What's the dot I put? Assume that's 1. So here we would say that it is at x equals 0, it is discontinuous because the limit does not match the function value. The limit is infinity. The function value is 1. Those don't match. And that's going to happen for any of our asymptotes. If we are approaching a vertical asymptote, it is discontinuous there. We learned that last year. That was an infinite discontinuity. Let's take a look at this one. The thing we are concerned about is 2. There's a border at 2. There's a discontinuity at 2, like this last function. That function's hiding in there. But let's take a look at x squared minus x minus 2 over x minus 2. If we were to factor the more complicated piece, so that piece is defined everywhere but 2, okay? If we were to factor that, we can factor out the x minus 2's and then divide, and then it just becomes this simpler version. So it's just a hole in a linear function. If we plug the hole in the correct location, so if this is the correct location, then we're fine. But what is this line defined at if x is equal to 2? Where is this line going if x is equal to 2? No, because it would be 2 plus 1. You're subtracting. 2 plus 1, it would be 3. So is it going to 3? No. Look what it's going to. What did they define it at? They defined it at 1. So if we were to graph this line, or this function, this piecewise function, so sorry. Let me start again. If I am going to graph this line, let me show you. It looks like this. Has an open circle at 2. And they plugged the hole down here. And they should have plugged the hole at 3. My graph is still pretty crappy, but they plugged the hole at 1. See this right here. So they plugged the hole in the wrong spot. So it ends up being a discontinuity there. The limit is 3. The hole was plugged at 1. They don't match. So that is undefined or discontinuous at x equals 2. And usually you just really are checking what's happening at the border. Is there a problem at the border? And that definitely has a problem at its border. If this said 3 there, they plugged the hole in the right spot for us, but it doesn't say 3. It says 1. Let's look at this one. We didn't talk last year too much about this function. This is called the greatest integer or step function. So let me draw it for you and then we will discuss it. Okay, that's kind of what it looks like. The steps are one length long. It is filled in at the integer and then jumps up, then filled in and jumps up. And so you'll notice at every integer, oh, that one is so in the wrong spot. I'm sorry. How about scooch that one over? That one gets here. There we go, that looks better. So at every integer, there is because you have to jump up to the next step. And so there is a discontinuity for the set of integers. So you could just write z, or you could say at every integer. Now, that's what this double bracket means. That means that's that step function. Here's how it works. If you plug in 0.2, it just takes off the 0.2 and it stays at 0. But as soon as we hit, now I wonder if my steps are in the wrong location. Anyway, I'll look at my endpoints, but you can see there's discontinuities at the integers. Part of me wonders if this is the closed and this is the open. I'll look into it and I'll get back to you because I forget. But it's just a weird level of steps. Hence why I always skip it. So there are 3 main types we're going to talk about for discontinuities. A removable discontinuity is one where there's a hole. One, they didn't fill it, or one, they filled it in this wrong spot. So a removable discontinuity, they just did not fill the hole, or they filled the hole in the wrong spot. So those are the graphs from above, okay? This one was A, this one was C. They filled the hole in the wrong spot here. Here, they never even attempted to fill the hole. Here is our infinite discontinuity because these are going to infinity, so we just call it an infinite discontinuity when we are heading toward a vertical asymptote. And then a jump discontinuity. Oh, they told me. See, I was wrong. Look. Closed in dot, open, closed in dot, open. Sorry about that. So there is your jump discontinuity. So we are going to have to know where those discontinuities happen, why they happen, you know, all that good stuff. Now, what's great is because of the limit laws, every function that is continuous at A, and if C is a constant, will continue to be continuous at A, whether you add the 2 functions, subtract them, multiply by a constant, multiply them, divide them, as long as the division doesn't result in a 0 denominator. So any polynomial is continuous everywhere, which is great. It's continuous on the real numbers. A rational function is continuous everywhere except where its denominator is 0 or it is continuous along its domain. So if a rational function is defined there, it's going to be continuous there. So remember, a polynomial like x to the 5th minus 4x squared plus 3x minus 2, that's continuous everywhere. If you put it into Desmos, it's a perfect little curve. You never have to lift your pencil. Rational function. So if you have something like x plus 2 over x minus 1, what's the only value that it is not defined? Where the denominator equals 0. And what value is that for this particular function? 1. So it is continuous everywhere but 1. 1 is the only number not in its domain. There's a piece to the left of 1. There's a piece to the right of 1. It is defined and continuous everywhere. So there are some things you can just look at and go, yep, that's continuous. If it's a polynomial or a rational function somewhere along its domain, it will always be continuous. Functions to be concerned about. Functions where you have a piecewise function where your pieces are just not matched up right. Vertical asymptote values, those are the places where we have to be concerned. Those are the places of concern. So polynomials are great. Rational functions are really great, except for that undefined denominator values, wherever your denominator equals 0. All of this is leading us toward doing something called a derivative. The more we know about limits, the derivative is going to be kind of a complicated limit. And so the more we know about limits, the better it will be for us when we get to derivatives. So it is leading us somewhere. So the following types of functions are continuous at every number in their domains: polynomials, rational functions, root functions, trig functions, inverse function, exponential functions, and log functions. Their compositions will then also be continuous on their given domains. Here's what you got to remember. What are the domains of these functions? Then by default, you get the continuity of these functions. So polynomials, they work for everything. Rational functions, we've talked about. On the domain is going to be everything but where the denominator is 0. Root functions, if they're square roots, we can only have positive values. Trig functions, think about our trig functions. Sine and cosine works everywhere. Its function is continuous. Once you start a sine or cosine wave, it's going to be continuous, but not tangents. Tangents have some issues, but if you know where it works, then you know where it's continuous. We're going to talk a little bit about inverse trig functions and exponential and log this year. Not a ton, but a little bit. But lots of functions are continuous everywhere. That does mean that there is a piece of the graph there. So the graph is defined there, it works there, it's great there. So let's look at this example. If you are trying to find the limit as x approaches -2, since this is a continuous function, the only value that we have to be concerned about is if we get a 0 denominator, okay? So if you think about 5 minus 3x equals 0 at a value of 5/3, we aren't plugging in 5/3. If we were plugging in 5/3, we would be concerned. But this value here is a continuous value. If it's a continuous value, we get to just use direct substitution. The limit is the function value. So this is just going to be the function at -2. That's what's great about knowing it's continuous at -2, because the limit is the value at -2. So I can just plug in -2. So I get -8 plus 8 minus 1 on top. I get 5 plus 6 on the bottom. I get -1/11. I don't know. That's what it is. It's approaching that value from both sides. That value is not an issue. This is the value that is not in the domain. That is the only value we can't use direct substitution for. Everything else is going to be great. If we try to plug in 5/3, that's the one that messes up. Everything else is fine. So really, we only have 1 point out of an infinite number of points to be concerned about. Everything else we can use direct substitution. So I've always been a person to try direct substitution. It says, where are the following functions continuous? Okay, let's think for a minute. X squared is a polynomial. It's continuous everywhere. Sine, that wave goes on for everywhere. So it is continuous everywhere. So the composition is continuous everywhere. Nothing screws it up. Nothing messes it up. Our first function is continuous everywhere. If you were to put it into Desmos, you would see it looks a little weird, but it keeps waving forever and ever and ever in both sides. Does that function have any breaks in the graph? No. If you put your finger down in one spot or your pencil down in one spot, you would trace it for the rest of your life without ever lifting your pencil. And that's a good way to think about what the graph should appear like in a continuous function. Let's take a look at this next one. Now, this is okay everywhere. So its domain is all real numbers. It's continuous everywhere. But the natural log is not. One of the things you have hopefully learned is that you can't evaluate a negative natural log. So this domain is where this stuff is greater than or equal to 0, where it's positive. So where is the cosine of x greater than or equal to -1? Ooh, the cosine has fixed the problem for us, right? Where's the cosine greater than or equal to -1? Well, it's always some value between -1 and +1. It's always. So this is okay. So the domain of this happens to be all real numbers. So it is continuous everywhere. Both of these, because of what is inside of them, it didn't mess them up, it didn't hurt them. Because 1 plus cosine, think about the graph of that. The graph of that would be the cosine function lifted up 1. I'm sorry, I won't be able to make it, but it's up here. No, it's not. It's right here. It looks like that. I don't know, but it is above -1. So if we were to plug that into Desmos, so if we put the natural log if I know where the natural log is, there it is. The natural log of the quantity of 1 plus the cosine of x it's still it still works, okay? So that is example 4. Okay. We do have some functions like a square root function that might be continuous from the right or continuous from the left only. So if the limit matches the function value from the right, it's continuous from the right. If the limit value and the function match as we come in from the left, then it's continuous at the left. Some are like that. Example. Our square root function. It is not continuous at 0, but it is continuous as we approach from the right. So it has right continuity. So this is continuous from the right at 0 because I'm coming into the right location, but I land there. But do I have anything from the left? I do not. Now a cubic function, a cube root function is fine. It is continuous everywhere. But a square root is only defined on the positives. So because of that, 0 is only continuous from the right-hand side. So that happens sometimes. And that's if one side is defined and one side is not. And one side you can come in from and one side you can't. So continuity can sometimes be just thought about from the left or from the right of that particular point. Yeah, we'll stop here. There you go. We'll continue this tomorrow, and there's a good chance this particular homework. So maybe your 2-3 will be due Saturday, but your 2-4 might not be due until Monday. I'll fix it. I will fix it for you.